Okay, guys, we'll be starting in 1 to 2 minutes. So, if anyone wants to join, your friends, you can ask them. All right. I think most of us have joined, so I think we should start right now. So, let me share my screen. And same with Discord. Let me share my screen really quickly. All right. So, is my screen visible to all of you? Okay, Chinmay says good afternoon. Good afternoon, Chinmay. Aditya says yes. Anubhav says yes. Okay, says yes. Mohit. Okay, all right. And over at Discord, Tavian, is my screen visible? All right, maybe I should not single you out like that, but I believe it should be. All right. Okay. So let's start. So welcome everybody to our second session of Gemini Study Jams. And in this session, we will be tackling the practical side of fine tuning. So, last session, as you might know, we were studying um, a lot of the theory, even though on a high level, we were studying a lot of the theory behind fine tuning. So, we were studying what is fine tuning, what are its types, right? When we should fine tune, what is the ideal use case for fine tuning, when we should not fine tune, what is not a good use case for fine tuning, and things we should keep in mind while we implement fine tuning. And we at the end we did go over a bit of code, but that was not a lot. But all right, we did something. So in this session, I would like to keep my focus more on code, but there is a lot of theory still that we need to cover. So the design of the session I'll clarify later, but just know that we will cover both a lot of code and we will also do theory. And at the end, if we have the time allowance, We can also go over, so in your syllabus, there is a Google app that implements fine tuning. We will also go over that, and I'll explain every block of code, what we're doing over there, and um, what is actually being done. All right. So if that sounds good, I think we can begin. So, all right. So the first slide over here is what will we do today? So as it is written, the main loop of the session will be, we will look at code, then wherever we need to stop, take a breath and understand what's going on, we will come back to the slides. So the main loop will be code, then theory, and then code, and then theory. It will be structured like this. So as I've written here, we will work through the given code and stop and understand the theory behind it at exhibitions. Right. And if so, the third point is for after the session, if you want to self-study, it is recommended that you have your Google Colab instance open along with the slides. All right. Yeah, am I all clear? Is there anyone who does not understand this? Because we are just starting. Believe me, we will be studying a lot of things here. So this is the least basic. And over at Discord, I think I should be fine. All right. Okay. So let's move on. So first of all, as I said, we will be going with code. So let me share that with you. Let me switch from this screen to code. All right. So is my Google Colab instance visible to all of you? Okay, it says yes. Okay, all right. Okay, Anubhav as well, Aditya as well. Okay, all right. So now let's go through everything over here, and we will try to understand what we're doing. So first of all, the aim of the session is of course to actually fine tune something. And as I said, the type of fine tuning we will be focusing our efforts on is parameter efficient fine tuning using the method low rank adaptation, LoRa, which is currently the most famous way to fine tune. So this entire notebook is themed around that. So first of all is the setup block. So this block is nothing but this is just a block that will help us later down the line. So this just has, so this is just Python. This is straight Python colors class. You do not need to pay attention to this. This is just so I can print fancy print statement, so I can inject color to my print statement. So if I so for instance, if I'll give you an example of what this does. So if I write something like f, and then if I write something like colors dot red hello. So what this class does is that it will inject red color. So as you can see, the output is in color red. So this is not related to machine learning. This is just an aesthetic improvement that I wrote. So nothing to worry about here. So now the second column of this is our data set. And I think with this data set, I should tell you what we are aiming for. So the aim is we will be having a base model, which I have selected as Quen. We will get to that, our model. And we want to fine tune it so that it can answer our queries so in a way so that it talks like Shakespeare is our aim. So as you can see, the input and the output for each entry in the data set is translate to Shakespearean, a sentence, hello, how are you today? And then the output is what we expect the model to, give back to us. So for example, the output here is good morrow. How does thou fare this day? All right. Is the aim clear? So what we are trying to fine tune for? I'll just say again, we are fine tuning a model so that the outputs it gives us are, so essentially it talks like Shakespeare is our aim. So it uses that kind of vocabulary. Am I clear on that front? Okay, says it's clear, and Anubhav as well. All right. So if that is clear, so first of all, why are we doing this? So as I explained in the previous session, this is a good use case for fine tuning because of a few reasons. So of course, the first reason is that this is not adding any new information to the model. So I'm not making it fetch new data. this is something that is already in the model. So mostly all large language models, these days, no um, no they have been trained on lots of text, so large corpuses of text, and one of those texts are all the works of Shakespeare, Hamlet, Macbeth, all of that. So that is already present somewhere in the model, the literature of Shakespeare, but it is latent. It is not the default way of talking for any large language model. So our aim with this fine tuning will be to bring out that latency and make our model answer in a way that resembles Shakespeare. And this is a behavioral change. It is not affecting the architecture of the model, and that is why this is a good use case for fine tuning. And we did go in depth why what makes a good use case for fine tuning. So if you want, you can check out the previous recording. um, but all right, so this is a very small example as well. I only have 50 data points here. Each one, as I already explained, is a key value pair. So all right, so time for a bit of Python. So this is just a list. This denotes a list. If you don't know in Python, these square brackets, this is a list of dictionaries. So this is a dictionary. In other languages, you call this a JSON object. So right, but in Python, we call these dictionaries. So a dictionary has a key value pair, and each entry in the data set is in the form of a dictionary. So a data set is a list of dictionaries, and each dictionary has one data point, with which is, so it has an input key with the value, the query of the user, and an output key with the value what we expect our model to return. All right, so that is the structure of the data set. We have 50 data points over here, nothing fancy. So we will get to some more considerations around our data later on. But right now, just know that this is our data set. And so the third code block in our setup block is just this library download. So this command does nothing except, so pip is the package manager for Python. And this exclamation mark, as I've already previously explained, is used to run commands in a notebook environment, right? So I write exclamation pip install -q. So what does -q does? It is just a flag. So it does not show me the output of this block. That's all it does. So Q stands for quiet. So it will quietly install all of these libraries. And the libraries we will be using are transformers, torch, PEFT, accelerate, and anops. So I'll get to why we are using each library and what it does. But so transformers library is the main library we will be using. So transformers is from an open source initiative called Hugging Face. It is a very great initiative, and this library makes the easier gives us the easiest way to fine tune. That is the main reason I've gone with this. And PyTorch is very important because a lot of the infrastructure built in transformers relies on infrastructure already present in Torch. We will get to what exactly each library is doing. Now, PEFT is the specific library that gives us fine-tuning abilities. So PEFT stands for, as we have discussed in previous class, parameter efficient fine-tuning, where we only fine-tune a subset of all the parameters we have, right? And accelerate is for, so this collab notebook uses a T4 runtime. So accelerate is for accelerating the training process. All right. And INOPS will get to those libraries. But I hope this is clear, the basic structure, all the libraries, right? And so with this, we get to our first piece of code, which is actually important, and our first exhibition. So the structure was, we will first look at the code, and then we will look at what it is doing. All right. So exhibition 1 says LoRa decreases the amount of parameters to train substantially. So as we discussed, that was the entire point of this. The entire point of doing parameter efficient fine tuning was that we do not have to, retrain our entire model. That is why we were doing fine tuning, if you recall from the previous section. And LoRa does just that. So before LoRa was mainstream, we had other methods of fine tuning. One was, we would add another layer on top of our transformer architecture, which was called adapter fine tuning. And another was, we would use instructions. So all of that, but that is not our concern right now. Right now, let's look at the code here. So the first line is importing from transformers. We are importing this factory class, which is auto model for causal LM. So what this does is it automatically gives me the language model if I know its ID. All right. So for example, it is used here. Model is equal to auto model for casual. LM stands for language model dot from pre-trained. So what this line will do, this line selects a model with ID, model ID, and device map. We'll get to this with ID, model ID, and loads it into this variable which I have named model. So this is just loading the model, and the model we are choosing to use today is Qwen 2.5 3B instruct. So the 3B stands for, it has 3 billion trainable parameters. Now this is I'd call this a medium range model. It is not too big. So for instance, if you don't know how big language models get, GPT-3 has 175 billion trainable parameters. So 3 billion is nothing compared to that. So this is, not that big, but it is still, so this is just enough where we can see our changes, but not so big that we will be unable to train in this session. So that is why I went with Qwen 2.5 3B. All right. And it is, of course, an inference model. So inference model means that I ask it a query, it gives me a response. All right. So we have the model ID as Qwen 2.5B, and we load that model using the auto model for causal LM. And what does causal LM mean? So the term causal language model means, so causal means simply means you give it an input, it takes the input, it uses that input to generate the next token, and so on. That is what is meant by causal. So you might think that, isn't that obvious? That is the only use case for language models. But no, there are lots of types of language models. Generative is not the only type, is what you need to keep in mind. That is why there is this factory class auto model for causal LM. So we are loading the model here. So now you'll see this line over here. So let's start. So that was the first line. The second line is from PAFT import LoRa config, task type, and get PEFT model. So all these are, so LoRa config is the class that allows us to define the configuration of LoRa. We will get to what each parameter means, but that's what you need to know right now. And task type is, this is just used to define what we are trying to do with our model. So over here we have defined that what we are trying to do is causal language model. So that just means inference, that I give it an input, it gives me an output. And get PEFT model is used over here, which takes our model, which takes our configuration of low rank adaptation, and it gives me the low rank adaptation corresponding model. All right, so let's read this code. So first of all, device is equal to torch.accelerator.current accelerator. So what this line does is, essentially this line is saying that if we have an accelerator available on our GPU, use that. That is all it's saying. So as you can see, if has attribute accelerator, then use it. So this is where also the accelerator library comes in. So what this does is, if you have an accelerator on GPU, it will use it and your training will be faster. Otherwise, just go with standard GPUs, CUDA. And if you do not have a GPU, you just ignore all of this and you just write CPU. But since our Google Colab runtime has a GPU, we will use that. And we will go with torch.accelerator.current accelerator.type. So, but the runtime does not have a, so it has a GPU, right? So that's what you need to know. So this is just for faster training. Then we have the model ID. As I explained, we were using Qwen 2.5. And then we load the model, right, from pre-trained models, model ID, and device is equal to map, device map equal to device means. So there are multiple types of models. So if I were running on a CPU, I would get the model from Hugging Face that corresponds to the CPU config. But right now I'm using GPU. So usually we just write device map equal to device. So first we just define what a device is. It can be CPU, GPU, accelerator, and then everywhere we use device, which tells Hugging Face that we are actually using GPU. So give us the model that is most suitable for GPU. So Qwen 2.5 3B instruct will have multiple versions. So we are getting the one that is compatible with GPU. So essentially it will just use PyTorch tensors is what this means, but we'll get to that. And then we have the PEFT config, right? So now here we are configuring our low rank adaptation. So now this is just a sample. So what does R mean? What does LoRa alpha mean? We will get to this. This is a separate topic. Right now, you need to focus on task type, which is causal language model, which is, as I've said, inference. And target modules has been also commented out, and they have written over here optionally indicate target modules. So this also we will get to what does Q projection, V projection mean. We'll get to this because this is separate. All right. So we have defined our config that we want R16 in our low rank adaptation and we want alpha 32. Now we get the PEFT model corresponding to our model with this config. So what this line is doing over here is that it is getting a Quen 2.53b with LoRa config, which we have defined. All right. Is this much clear? If there's anything you need to ask, you can ask right now. I hope it's not too confusing right now. Mohit says clear. Aditya and Nandini as well, clear. All right, so if you understand this, Kanika says, can you please repeat the R equal to 16 part? I lost connections. Okay. And Hoker says clear. Okay, all right. So Kanika, what I meant over here, R equal to 16 and LoRa alpha is equal to 30. So these are called hyperparameters. We will discuss them later down the line. Right now, you do not need to focus on them. What you need to know about R and LoRa alpha is that these are the parameters that control the fine-tuning process. That's all you need to know. We will understand them in detail later down the line. Okay. Okay, all right. Let's move on. So now this is the interesting part of it. This is the part I want all you to know. So now I'm getting, so we have got the Quen 2.53b model with the appropriate LoRa config that we defined. So now let's see what advantage do we get for using LoRa. So over here, I've extracted trainable parameters and all parameters. So there's a function get NB trainable parameters of the model class, which gives me two things. So first of all, it will give me the total parameters the model has and the amount of parameters LoRa will be training. So these are the two things this will give me. And those two things I have stored in these two variables, which I have called trainable parameters and all parameters. And so I'm calculating simple percentage formula that out of the total parameters, what percent of them is LoRa going to train? So this is a simple mathematics formula. Trainable percent is trainable parameters divided by all parameters into 100. Simple mathematics, right? So now, and then I have printed this. So let's look at the output over here. So as you can see, the total parameters for Quen 2.53b are 3 billion, as we discussed. So this is 3 billion, 8 million, 962,000, 3 billion, 89,625,088 total parameters. And the total trainable parameters are a very small fraction. So the total trainable parameters are only around 3,686,400. So you will observe over here. So using LoRa, the amount of parameters we have to train is only 0.11%. In full fine tuning, we would have to train all these 3 billion parameters. But since we are using LoRa, supervised fine tuning, PEFT, we only have to train a very small percent. It is not even 1% of the total amount of parameters. So this is the advantage of using LoRa. And I hope this is clear. Hey, Anshu, can I get the recording? Yes, Naman answered your question. Okay, it says clear. All right. So with this, we are at our first exhibition. So now I'll need to switch to my slides because we need to talk about something over there. Okay, let me share. All right. All right, my slide should be visible here. Right. So the first exhibition is LoRa decreases complexity. So what does this mean? So let's read this line by line. I'll explain this to you. During full fine tuning, the model is initialized to pre-trained weights phi and update it to phi plus delta phi by repeatedly following the gradient to maximize the conditional language modeling objective. So what does that mean? This simply means that, so as I explained, large language models are nothing but giant next word predictors. Each word in a sequence has a probability of getting selected. So what this line means that after we fine tune, the probabilities change from initially they were phi to phi plus delta phi, where delta phi is the change in the weights. So if this is too mathematical for you, just know the intuition is that we started with weights phi initially. So this word has this probability of getting selected, this word has this, and we ended with weights phi plus delta phi, where delta phi is the change in weights. All right. The second point is, one of the main drawbacks for full fine tuning is that for each downstream task, we learn a different set of parameters, delta phi, whose dimension equals phi. All right. So what this means is, as we saw, we had 3 billion parameters. So one huge disadvantage for full fine tuning is that every time we need to specialize our model for a downstream task. So right now we are specializing to talk like Shakespeare. If we had to specialize for something else, to be a legal assistant, or uh, if we had an image model to produce anime aesthetic images more and all of that, every time we would have to train all those 3 billion parameters. So that is a very huge disadvantage during full fine tuning, right? And this means that for each task, for a model like GPT-3, as I said, GPT-3 has 175 billion parameters. Storing and deploying many independent instances of fine-tuned models can be challenging, if at all feasible. This just means that for very large models like GPT-3 with 175 billion parameters, we cannot individually fine tune for every single small downstream task. That is a very huge disadvantage of full fine tuning, and that is why we resort to techniques in parameter efficient fine tuning like LoRa, right? So there is this visual over here that I made to help you understand. So this is our pre-trained model. So this is before fine tuning. It says that, let's say we have a sentence, today is a dash day. Before fine tuning, let's say we had 3 words. Today is a sunny day, today is a rainy day, today is a windy day. Each word had some probability, 0.33, 0.33, 0.34. All right. And so these are the weights, 5. After fine tuning, I fine tuned my model to choose sunny exclusively for this sentence. What happened is that today is a dash day. Now sunny has a greater probability, 0.6. We started with 0.33, now it has 0.6. And rainy and windy have decreased probability, 0.2 and 0.2. So after fine tuning, the weights change to 0.6, 0.2, and 0.2. And the difference between the final weights and the initial weights is delta phi. So this was what I was saying in the previous screen. We start with weights phi, and the change in those weights is delta phi, and we end with the weights phi plus delta phi. Is this much clear? I'd like to take your input first. Gurdeep says it would have been ना से ही है तो I don't understand you, Gurdeep. I'm sorry. If you can. Nandini says it's clear. Okay. All right. So if you want to ask anything, feel free to ask. I'll answer all your queries. All right. But right now, okay, Ankit, also Anubhav as well, Chinmay as well, it's clear. All right. So since this is clear, Hokesh asked something, how LoRa selects which parameter to train on. Okay, Hokesh, good doubt. And we will get to this point as well of how LoRa selects. We will get to this. It is later down in the slides. All right. But right now, what we need to understand is that we are only training a fraction of what we would and how basic fine tuning should work. Okay. All right. Right. So now I have written here. Now imagine this process for the 175 billion parameters for GPT-3, and even more in the latest version. So this is just not feasible. All right. So what does LoRa do here? It decreases complexity. All right. In LoRa, the task-specific parameters increment delta phi is a function of theta, and it is encoded by a much smaller sized set of parameters with the size of the parameters much less than the size of the weights. So what this means, let me just explain to you. So okay, Sarthak asked something. What is phi? Could you please explain again? Okay, all right, Sarthak, I'll explain again what phi is. So all right, so as I said, as we also discussed in the previous session, that language models are nothing but giant machines that predict the next word in a sequence. So if my sequence is today is a dash day, the model assigns to every single word in the English language a probability that this word can be the word I need to generate. So as an example, I have taken three words. Let's say the model's vocabulary had three words: sunny, rainy, and windy, right? So what a language model does is, so we are skipping over a lot of the architecture, we're skipping over a lot of the statistics, but on a high level, what a language model does, to every single word in the English language, we have an assigned probability, right? And using those probabilities, we select a word. So initially, every word in for this particular instance has equal probability. So I have a 1/3 chance of selecting sunny, 1/3 chance of selecting rainy, and a 1/3 chance of selecting windy. Today is a sunny day, rainy day, or windy day. All right. Now, what is phi? Phi is these weights, the probability that a word is selected in a generative model. Is that clear, Sarthak? Phi is just the probability that the words are selected. So for this instance, phi is 0.33, 0.33, 0.34. And another point is, so this is just basic probability, but I'll just clear it out in case you don't know it. The sum of probabilities always equals 1, right? All right, so let's talk about how LoRa decreases complexity. So now this is a bit mathematical, so I'll try to explain this to you as best as I can. So as we said, during full fine tuning, we had to retrain in a way the entire model, the whole model, the entire set of parameters was being fine tuned. So in case of GPT-3, which had 175 billion parameters, we were fine tuning every single one. Now that is very efficient. Now, what LoRa does, so as I said, we transition from the weights phi to weights phi plus delta phi, where delta phi is the change in weights. It is the change in probabilities after fine tuning. As in the above example, since we wanted sunny to occur more than the other words, we fine tune so that sunny will have more probability. So its probability increased. So that's what fine tuning is essentially doing. At the end of the day, fine tuning just increases the probability of using words that we want the model to use. So in mathematical terms, what is being said here is that now the change in the weights is important, because if we are essentially changing the weights in full fine tuning, the change in the weights has a dimension of the parameters of model. So for instance, in GPT-3, the change in weights will have a dimension of 175 billion. But what LoRa does is, and so the researchers behind LoRa found something very important. So what they found is not each parameter contributes equally. What does that mean is that a lot of the, so they looked at the matrix delta phi, so they looked at the weights after changing them, and what they observed was that a lot of the weights don't get changed a whole lot. A lot of the weights remain same, and the matrices are very sparse. So what they inferred is that not every parameter is contributing equally. A very small percentage of the parameters is contributing a lot, and we can exploit the fact to not train every single parameter but only a subset. Now, how is that subset selected? So what it's saying is that LoRa replaces delta phi as a function of theta. What that means is that instead of 175 billion size of the matrix, we get a very, very small size, which is a small fraction of the original size, is further encoded by a much smaller size set of parameters. So it is written that the size, so if you did not know, the straight bars are used to indicate in mathematics the size of a matrix. So they are saying that the size of the matrix used by LoRa, which is a function of theta, is much smaller than the size of phi. I hope that is clear. And the second point is that when the pre-trained model is GPT-3, the number of trainable parameters can be as small as 0.01% of size of phi. Is that clear, or should I explain this a bit better? It's clear to Hokesh. Everyone else, is this clear? Manav says I need to explain. Okay, all right. Manav, I'll explain this too. Okay, explain this to. What is the role of function? I didn't understand. All right. Okay. So, okay, I'll show you something for you to understand this. Just wait a minute. Wait a second over here. Just wait a second. I'll open something. My wish Anand says, does LoRa work for fine-tuning Gemini and other LLM models as well? Yes, Anand, it works for every major language model that uses the architecture that we are targeting. So the transformer architecture, and there are other architectures as well, and it works on those as well. So the short answer would be yes, it works for every single one. Right, so now let me show you something. Now my OneNote screen should be visible. Right, so I'll try to explain this to you. So very small example. Let's say this is phi. What is phi? Phi is the probability distribution for the next word. What I mean by that, as we were talking, that every word has some probability to get selected, right? And that is represented by phi. Let's say we have 3 words, right? So let's say the weights for this. So this represents the first word in my alphabet, the second word, and this represents the third word. So what this means is I give an input sentence to my language model. It does some processing, and after that processing, to each language word in the language, it assigns a probability that this is the probability that the next word in the user's given sentence will be this word. So is this clear? So what? So I'll take it step by step. Is this small step clear? That what language model does? We give it a sentence, it does some processing. What that processing is, we don't care about right now. What we know is that it converts, does some processing, and assigns a probability to every single word in the language that this specific word is the next word for this sentence. Right, Sarthak says it. Okay, says yes. All right. Now this right here is phi. Okay. So the goal of fine tuning is to change phi by adding another matrix delta phi such that the weight distribution is in our favor. What that means is that the words we want to appear more frequently are assigned a higher probability of getting selected. So let's say I wanted my word 1 in this language to get selected more frequently. So its probability will increase to, let's say, 0.6, and the probability of the other two will decrease to, let's say, 0.2 and 0.2. Is this clear? So the essential aim of my fine tuning is to go from phi to phi plus delta phi, where delta phi is the change in the probabilities. Manav says, I can't hear you. Reload the tab. Naman says, okay, all right. Manav, just reload real quick. You will be able to hear me. Meanwhile, okay, this is clear to all of you that what we're doing with this. All right, so this is the aim of fine tuning. So what do I mean? So now what you will observe is delta phi is the change in the weight. So let's see. How do we calculate delta phi? So the probability of selecting word 1 went from 0.2 to 0.6. What does that mean? That we increase the probability by 0.4, right? And the probability of selecting word 2 went from 0.2 to 0.2. That means there is a change of 0.0 for selecting word 2. The probability of selecting word 3 went from 0.6 to 0.2. That means the probability decreased by minus 0.4. And this matrix which we form is called delta phi. Is this much clear to all of you? How we calculated delta phi? All right, Sarthak says it's clear. All right. Right. So this here is delta phi, which is the change in my probabilities. Now, the important thing to observe here, the takeaway here is the dimension of my word matrix for this example was 3 rows and 1 column. And the dimensions of the output phi plus delta phi is also 3 rows and 1 column. So if you don't know, rows are these horizontal section, row, 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 and columns are these vertical sections, column, column. All right. So the matrix has 3 rows and 1 column, and the output also has 3 rows and 1 column. And delta phi also has 3 rows and 1 column. Is that clear? Yes. Okay. All right. So this is all a game of dimensions, and this is what much of machine learning is about. So what we observed is that delta phi also has dimension 3 cross 1. So for a model like GPT-3, has 175 billion parameters, right? Let's say they translate to, so I think the amount of words in GPT-3 is around 50,000. So GPT-3 can generate 50,000 words. So every single word, A, B, C, A, and to every single character, question mark, exclamation mark. The vocabulary of GPT-3 is 50,000 words. So now let's assume our input. So since we have 50,000 words, we need to assign a probability to each word. That means in case of GPT-3, my phi will have some dimension of 50,000 times some number. So we will not focus on the second number. This is more than 1. I'll just tell you that. Which means the change in the weights will also have some dimension, 50,000 rows and then something, something. Is this clear? Yeah, this means delta phi will have same matrix size as phi, right? So now you can imagine delta phi also has 50,000 size, right? So what LoRa does is that in full fine tuning, to get this matrix delta phi, we would have to go through 175 billion parameters in full fine tuning, right? But what LoRa allows us to do is we break down delta phi such that, so we observed that not every single parameter is contributing to our fine tuning process. Not every single parameter is as important. So what they observed is that the change was 0 for a majority or very less for a majority of the parameters, right? So what LoRa allows us to do is that it allows us to break down delta phi into two matrices A and B, which have some dimensions R cross D, where R is much, much smaller than D, which just means, so instead of, so D here is 175 billion because that is the amount of parameters, right? So what we are doing here, so I'll explain this to you. So what we're doing here, so what LoRa does is that we, instead of, we calculate delta phi in a way that decreases the amount of parameters we consider and hence decreases the computation process significantly, is what I'm trying to say. This is a bit of mathematics that we have. We decompose it into A and B, where they have dimension R, which will be much, much less than the dimension of D. That's what I'm trying to say. Now there is a bit more nuance, but that is what we are trying. What I'm trying to get at. So is that much clear? Okay, Manav says yes. Sathak also clear. Hokesh clear. Nandini clear. Okay, all right. Kanika says, please explain again. Okay, Kanika, I'll go over this once more. All right. So I hope you understood this much that we changed our probabilities, right? So our aim is to, in any fine tuning process, is to go from phi to phi plus delta phi, right? The change. So what we need is we need delta phi. This is our aim. We need to get this. How will the, the probabilities change for each word? So we need to get this delta phi. Now, how do we get delta phi? This is where we differ in FFT, full fine tuning, and PEFT. In FFT, we get this through some process. I will not go into the detail right now. Through some process where we process a very huge matrix that considers all 175 billion parameters we have at hand. Whereas in PEFT, to get to delta phi, we only consider a very small fraction of the entire parameter list. So let's say instead of 175 billion, we only consider like 35 million. That is the gist. Is that clear? Okay. And so just wait a minute. And so before we proceed, I'll just so I don't think we will be able to cover a lot right now, but um, I'll just introduce something to you. So those of you who want to go into like a lot of detail into low rank adaptation, this was the research paper that introduced the concept of low rank adaptation. This has every single detail you might need. So there's a lot of mathematics. So you will not understand this maximum phi summation, but there's a lot of text as well. So if you want to really go into detail of how this works, you can just read this paper. It is a very mathematical need. So for that, you will need a lot of background. First, you will need to understand how transformers work, the architecture. So what is an attention layer? What is a feed forward layer? What is a decoder? What is an encoder? And then you will be ready to read this. But just in case anyone wants to go into depth, they can read this research paper. I will link this research paper in the references after the session. All right, so let's move on to our slide. All right, okay. So I think we are all clear on the fact that LoRa decreases complexity. How it decreases complexity is a black box for right now, but it decreases complexity. So now let's get back to code and see what actually we'll be doing next. All right, so we are past this. Now, let's see. Now I'll go over a bit of code. So let's try and cover a lot of code and then we can get back to theory because I promised code to you guys the last session. So I've marked every step with an integer here. So first step is to load the model. We already did this. This is just a repetition of the last step. So the same thing. So first select a device. It can be, it can be straight up CPU. It can be GPU if you have a GPU to use, and if you have a GPU with accelerators, that's even better because that makes the training process go faster, right? Model ID, we have chosen Coin 2.5 3B instruct. This can be any model, so you will need to reference the Hugging Face docs if you want to get a comprehensive list of what models are, but you can use GPT-2 here. That is also a good one. So this GPT-2 is not actually powerful, but it's a good model. There are a lot of, so you can use Flan T5 model. So you can use BERT here, BERTA, right? So there are a lot of models you can use. So you can do your market research on this, but what we are going for is Qwen 2.5 3B. 3B stands for 3 billion parameters, which is very less compared to even GPT-3, right? Loading the model, as I explained, auto model for causal LM from pre-trained, get this model from the class, and we load our model into the model variable. Set up the configuration for our LoRa process, where R is 4, LoRa alpha 16, what these parameters actually are. We will get to them. And target modules are Q projection, V projection or projection. This is what we'll study next, what these are, all right? But right now I'll try to cover some code, all right? And then we'll get to this. Then we get the corresponding model with the correct LoRa config. And this is just to save our model. So actually you can save the, so right now when I do this get PEFT model comma PEFT config, so what this does is, so right now you'll see we have not trained it on any data, but I'm just calling get PEFT model. I'm just getting the model with the correct configuration. So what this means is that it will get me the LoRa model, but there is no data fed into it. This model can be fed any kind of data for any type of task that we wanted to do. And that is also another advantage. Now that I have this model, which has very less trainable parameters as compared to the entire 3 billion, we can train it on any sort of data. And I can actually store the untrained LoRa model and I can use it later, right? So this is the advantage. I'll also cover this cell, then I'll take your doubts, right? So this is also nothing new over here. We are just checking, doing a bit of analytics before we actually get to fine tuning. The total parameters are 3 billion. The total trainable parameters are a very small subset, which is just around, this is just 1,511,424, which is 0.04% of the model. So you can see what a substantial decrease this is. All right. So these two code cells, anyone, any doubt? Look at the code. If you have anything to ask, I'll clarify it. Anubhav has a question. One question: can we use Google Colab directly from VS Code? I think so. There is an extension. As Mohit has answered, yes. So now you can use Google Colab directly from VS Code as well. Of course, everything depends on how powerful your machine is, right? If you have a powerful machine, so let me just show you something here. So my runtime right now is, so the runtime depends what kind of machine we are using in Google Colab. So you can use a CPU. This is the lowest one, and the freeware also allows us to use a T4 GPU, right? But with 8 years, I can get the A100 GPU and L4 GPU as well. Now, if your local machine has a GPU more powerful than this one, feel free to use your local machine because that will be better for you. Now, just be aware that machine learning libraries are often very huge in size. So there will be gigabytes of size, right? So just have that space. But if your GPU is better, go ahead and use your GPU because for the free version of Colab, there are a lot of restrictions. Sarthak says, where we have mentioned that we want to use a CPU/GPU. Sarthak, we have mentioned, so first of all, we have selected what kind of device we are using. So it can be, so as a CPU, GPU, or an accelerated GPU, all right? Now, where have we mentioned we want to use this device? So over here, you'll see I have set parameter device map is equal to device. So when I'm loading the model, the class knows that I want Qwen 2.5 3B model, which is able to use a GPU or a CPU or an accelerated CPU. So this is where how we are using that, mapping the model to the device. Okay. All right, let's move on. Okay, anyone else, any other doubt in the code sections? I'll just clear it and then we can move on to the next two code blocks. Okay, I think these code blocks are clear. So I think we can proceed to the next one over here. All right, so now this is the next step of our fine-tuning process. So some of you might already know this, but models don't take input in the form of words. They do not take input in the form of English or Hindi or any other language. Language models take input in the form of tokens. So a token is actually a collection of words. So let's say you have a sentence: the fox ate the cake, right? So what happens is that the language model will take this sentence and let me just comment this out. Will take this sentence that you inputted, then it will convert into tokens. Token will be something like so it will be numbers. if I had to say something. So each word will be represented in the form of a vector. So let's say something like this. This will be converted into tokens. And tokens, if we have to intuitively understand that, we can understand tokens. For example, one token might contain the word the and space. The other token might contain fox. The third token might contain this part. Then the fourth token this part. Then the fifth token this part. But in reality, they're not that clean. Tokens can be, overlapping. So a token does not correspond to a single word, but it roughly does sometimes, right? So our models take input in the form of tokens, and so that's why we need a tokenizer. A tokenizer converts from English to tokens. Right, the tokenizer we are using here is auto tokenizer, which is also from Transformers library. All right, lots of tokenizers available in the market. You can use any one of them. Our example is very simple, so we are using a lot of simple tools. Auto tokenizer is also pretty simple, right? So here, this is where we are initializing our tokenizer. So our tokenizer is the variable name is equal to get an tokenizer automatically. So the auto part means automatically in auto tokenizer, and here as well auto model for causal LM, right? So auto tokenizer from pre-trained. So tokenizer also, yeah, so tokenizer is not just a built-in machine which has strict mappings. A tokenizer is in itself a machine learning construct. So for the model Quen, load a tokenizer automatically. This is what this is doing here, right? And this right here is padding. I don't think we have time enough to go into padding, but essentially what padding is, let's say we have input has two sentences, um, a cap and then a bigger one, the dog ate the bone. So as you can see, the first sentence is smaller than the second one. So what we will need to do is our inputs need to be clean. So we need every single input to be of similar size. So what we add is we add padding. So there can be a pad token here. So we will add some tokens to the beginning or the end of the smaller sentences so that they become equal in length, so that every single token becomes equal in length. That's what padding is. What this line is specifying is that we want the padding to be done from the right side of the sentence. I can turn it to left and it will be done from the left side. But for Quen model and other models, usually padding is done from the right side. So right side means, so if this is a word, right side padding might mean, padding after the sentence finishes, right? So we have a sentence and after that we add padding tokens. For left side padding means padding before the sentence starts. That's the difference. For inference model, causal models, we use right side padding. So we are specifying the padding side. And this here is just let's just ignore it for right now, but this just means that if we do not have a padding token available, some models do not have a padding token available, then just use the end of sentence token as the padding token. All right, so is this clear to all of you? Just standard tokenizing. Okay says yes. Sarthak as well says yes. All right, it's clear to Nandini as well. Okay, all right, so I think let's move. Right. Now this here is a bit more interesting part. Now, before we are fine tuning, it is necessary that we first test the model on how it does without fine tuning. So of course, how can you know that the fine tuning process has done something? You can only know when you see results. That of course, so before I fine tuned, this was the result, and after I fine tuned, this was the result. Therefore, there has been an increase in whatever statistic we are measuring. So first of all, I have 3 prompts here. So keep in mind, this is not fine-tuned model, right? So we will test these prompts on the base model, baseline generation, right? So I have 3 prompts here. The first one, each is similar. We want to convert a sentence into Shakespearean style. The sentence is different. The first one is, hello, how are you? The second one is, the weather is nice today. The third one is that your pen? All right. These are the 3 sentences. This is just some Python here. So what we're doing, we are going over each sentence. So this is a list. We are going over each sentence. We are converting it into a token, as I said, the model will not accept English, it will accept tokens, right? So we use our tokenizer to convert our prompt into tokens. Return tensors PT means we want the whatever value the function returns to be a PyTorch tensor. What that means does not concern us right now. Dot to device means that I want the tokens returned, the matrix tokens are essentially numbers in matrices, right? So the matrix returned, I want it to be converted so that it can be used with whatever device I'm using, and the device I'm using right now was a GPU. So this is what this line does. So we got our input tokens. Now with torch.nograd, nograd just means uh, nograd just means that when we run our inference, the weights of the model will not be updated. That's so the overview. Just that much is enough for you right now. Torch.nograd means that we are not updating the models when we do this. Now if we use the model to generate on our inputs, max new tokens mean the amount of new tokens the model can generate, right? So if we have capped it at 50 tokens, we want no more than 50 new tokens in our output than the input, right? So we give our model the input, we give our model the max new tokens, and this is just, so you can ignore it, but right now let's just ignore it, and then we just print. So this is of course just bit of Python, so I just set it to blue color, then print before, then input. So let's see the output what we got. So all right, here's the, so the first sentence was hello, how are you? The output Quinn gave is, as you can see, it's not too good, right? Hello, how are you? How do you do? How do you do? How are you? Hello. This is a playful and creative rephrasing of the traditional greeting. Your original hello, how are you? So this is nothing to do with Shakespeare. So the style did not change at all, right? So not good. So the second was, so keep in mind, so you might think that this is very weak in terms of language models. Of course, it is weak. It has only 3 billion parameters. GPT-3, the lowest tier model that OpenAI still offers, is 175 billion parameters. So compared to that, this is very weak. But due to our necessity, we are using this model. So you can do the same process. It will not be the same process. It will be a bit different. But you can follow the same pipeline to fine-tune GPT-3, any model you want, right? But right now we are using this model, which is a bit weaker, but this is just well enough that we can see the changes, right? The second sentence was, turn to Shakespearean, the weather is nice today. What we got as an output, what a lovely day it is. Let us go out and enjoy the sunshine. Still not good, right? Can you suggest some activities we can do outside? Not good. We don't want this. Third sentence was, is that your pen? Now the output is, yes, it is. That's a great way to start a conversation. Here's an example using the Shakespearean style you mentioned. Is this the wand that oft has held thy breath? I tis my wand with which I do. Now this is a slightly more relevant. Of course, this whole part here is completely unnecessary. We just wanted this line out of this output, right? Yeah, is this clear? Is this baseline text testing part clear to all of you? All right, it is clear. And so you understand that why the Sarthak says, please repeat. Okay, Sarthak. So what we're doing here is essentially we are testing our model before fine tuning it on some sentences I have prepared. So these three are my inputs. I need to turn a sentence into Shakespearean style, right? Hello, how are you? The weather is nice today and it is at your pen. So what I do is that I go over every single prompt. I convert it into tokens because the model takes input tokens, not English. Then I get some output and I print the output. So we get this output. For this input, the model responded with this. For this input, the model responded with this. And as we can see, the outputs are not up to the mark. We wanted it to use Shakespearean language, which it has not used. Is that clear, Sarthak? Okay, all right. Okay, so let's move on. So now I also did this statement model.eval. So this statement, what it does is it just prints the specifics of the model. So as you can see, so this is not relevant to us right now, but as you can see that this is the base class is a PEFT model for causal LM. Inside that we have wrapped a base model, which is a LoRa model, which has wrapped the base Quen2 for a causal LM model, which has wrapped inside itself a Quen2 model. So there's a lot of layers. So we can also, so if you want to know the structure of any language model, you can just call this. So uh, the number of embedding tokens, the number of layers we have, what each layer is. So there's a module list. So there's 36 layers. There are 36 Quen decoder layers. There is a self-attention layer, Quen2 attention layer. There's a Q projection, which is linear. So this is inserted by LoRa. All right, so this is not relevant right now, but just to show you that you can actually just look at the specifics of your model using this command. All right, next step. Now it's time for pre-processing our data. We cannot feed our data as it is to the model, right? So there are some things we need to do before we actually train the model. So this is that step, pre-processing step, right? So this is a helper function. So what this function is doing is it's taking one data point and it is converting it into a string. So as I explained to you earlier, our data set is a list of dictionaries. The model takes a string, converts it into tokens. There is no mention of dictionaries or lists everywhere. So what this function does is that it takes a dictionary and it converts the dictionary into a string of the form this instruction, then whatever the dictionary had in the key input, then response, and whatever the dictionary had in the key response, right? Now, this right here, what this does, response start text dot index response plus slash m. So what this is doing is essentially, so we don't want, so every time we prompt our model, we don't want the model to give our prompt back to us. So if we just return this thing, it will, every time we prompt it, it will say to us instruction was this and then the response was this. We don't want that. We only want our response. So this just removes the instruction part from our text, right? That's all it does. And then we return our text and the response start. So I'll get to this later. And so this is straight up Python code. So somewhat advanced Python code. So what we're doing is, so first of all, we are calling this function format example x. For each data point in our data set, call this function format example, right? So each of the 50 points, data points, we will call this example. And what we will do is that we will take its value and we will zip it. All right, so essentially what's it doing? So this line over here will form a tuple of strings. Actually, let me just print this. So it's more clear to all of you. I should not have used this shorthand Python syntax, but all right, let's see what this will do. I have to print this as well. Okay, just real quick. Okay, while this is processing, let's move on. I'll show you what this does to you. But right now, what you need to understand is that what this entire thing is doing is that it's converting our data set, which is a list of dictionaries, into strings, list of strings that can be used by our model, right? Now what we do, we have got the entire data set as a list. Now we are turning that data set into tokens. So we use the tokenizer to convert the data set into tokens. Now there are a few options we can use. Of course, we want padding. So what padding does, as I explained, is that it makes every single token have the same length, which is important for our model. What truncation does is that, let's say we have defined some max length here, 512. If any sentence exceeds that length, cut it, because we want it to be of similar size, right? And return tensors in the form of PyTorch tensors, and return offset mappings is true, but we don't need this. This is optional, and we'll not go into much detail here, right? But all right, so what we take, so what we did here is we converted our list of dictionaries into a string. Then we used our tokenizer to turn that into tokens, right? And the tokenizer will return three things. It will first of all return input IDs, it will return attention masks, and it will return offset mapping. Now, what is this? It's a bit complex, but let's understand. So a tokenizer will return three things. So it not only turns our text into tokens, it also gives us an attention mask. So what is an attention mask? So the input ID should be clear. It is what the tokenization does. So this is the tokens of the text. What is the attention mask? The attention mask tells the model what words should be focused on in the text. So you might not understand this, but what that essentially means, so this goes into the depth of how transformers actually work. What attention does is attention tells us that in this sentence, this word relates to this word. So let's say that we have a sentence, I want a tutorial on machine learning. Now, the word machine learning should pay attention to the word tutorial, because the user wants a tutorial on machine learning, right? So that is what the concept of attention is, because machine learning can appear in any context. So machine learning can be defined like machine learning is the process of making a machine learn, or there's a quiz for machine learning tomorrow, help me revise for it, or I want a tutorial on machine learning. Every single one has a different context for the word machine learning. What attention does is that it tells us what word does our word machine learning relate to, what other words in the user sentence does our word relate to. And what an attention masters is that it tells us that these are the words that in simple English, these are the words that are worthy of attention. So we don't want question marks. um, so we don't want some words to attract attention, like, so some words are just there for example, punctuation marks. We don't really care about punctuation marks. No word is paying attention to that. So attention marks help us control that, is the gist of this. So I know this is a bit confusing, but just hang with me there. uh, is this much clear? I'll re-explain this. What we're doing here, we are taking a data set, we are turning it into string, we are encoding that string, and we get three things back from the encoder, which are input IDs, attention mask, and offsets. What is input ID? Input ID are the tokens. What is attention mask? It is what our words should pay attention to, but this mask tells us that these are the words worth paying attention, and we should not pay attention to the rest of the words. It's clear. Okay, says it's clear. Manav says it's clear. Kanika says, can you repeat the offset? All right. So Kanika is asking about what is offset mapping. So what is offset mapping? So offset mapping is actually that is something I'm trying not to go into detail into, because that comes more under a transformer architecture rather than machine learning, right? But because if we go into that, I'll go into detail over there. But all right, we can have a simple explanation. So what offset mapping does is, so let's say we have an input text, right? So so the encoder is giving us three things, right? And so what offset mapping does is that it tells us the span of each character in the text. So for example, we have a sentence, let's say it is transformers are fun, right? So after we tokenize a sentence, right, we get some tokens, right? We get the tokens, right? Now what offset mapping tells us is that how the tokens are mapped to the original string. So if we have a sentence, transformers are fun, right? So the initial sentence has transformers from index 0 to whatever the length of transformers might be. So transformers is transformers. So transformers is a 10-letter word. So the offset mapping for transformer will be from 0 to 10. So it's telling us, the offset map tells us where in the original text our token lives. So of course I'm simplifying it, but that is the gist. So offset mapping tells us where in the original text the token lives. Is that clear, Kanika, for right now? Okay, all right. So input IDs are the our actual tokens. Attention mask tells us what to pay attention to, and offsets are just where in the original text the token corresponds to. So I said transformers, I took it as 10 words, but as I said, tokens are not necessarily complete words. The token might cut off at transform, right? So then the offset mapping will be 0 to, so it's a 10 letter word, transform will be somewhere around 8 or 7, right? So that's the gist, right? All right. Any other problem in this blog? Let's tackle this. So don't be shy. If you want to ask anything, just ask away. This is the entire blog. What we are doing is we are formatting examples, right? And we are recording where the response begins. So why is this important? Why are we recording where the response begins? Because we do not want to um, want the model to also use the instruction for its fine tuning. That's the gist. Because what we want to focus on in our model is not the input. So what I mean by that is the input will remain the same. We don't want, translate to Shakespearean to be what we pay attention to, because when the model will learn how to map, how to reassign probabilities, we don't want, translate and Shakespearean to have higher probabilities, right? So we are not using them in our training. That's why we are excluding the instruction bit from the input tokens. So offset are like pointers. Yes, Hokesh, you can call them pointers, but they're not like pointers. You can think of them as string indexes. So not, a bit like indexes. So if transformers starts at index 0 and ends at index 10, we will get the offset mapping 0, comma 9. So I'll say that they're more like indexes. What if there are grammatical errors in the input part by the user? All right, Kanika. So if there are grammatical errors, so modern language models are, smart enough to understand them. So what do we mean by smart enough? We usually infer by the surrounding context what the user is trying to say. Common mistakes are usually, so if you take a prompt, what we usually do is we'll first manually check the prompt, using not machine learning, just regular uh, code. So if it's a very common mistake, so if a word is very commonly misspelled, we just hard code it, right? But for other words that may not be, usually misspelled, uh, we actually sometimes include them in the vocabulary um, of our model, because the data we train on is not always perfect. Websites can have mistakes, books can have mistakes. So when we train a transformer on the data, it naturally knows when we have made a mistake. So it will see, millions of examples of the correct pronunciation of a word. Then it will see an example of wrong pronunciation of the word, and it will understand that that is wrong, but it will be smart enough to understand the context. Okay, all right, let's move on. Now, training settings. Now here, so now we'll first of all, we formatted our examples, we did all of that. Now we are moving on to training settings. All right, so the task of this step here is to, tweak the dials so that the training goes how we want. So there are certain parameters we need to set. All right, converting our tokens to training data set. Now this over here, class custom data set. I say let's skip this for right now, but I'll try and explain this what this does in short, right? So for right now we have a synthetic data set. I have literally in this notebook I have created a list of dictionaries. That is not usually how you will get data sets in machine learning. Usually you will get them from sites such as Kaggle, or other sites, or Hugging Face as well, all those sites. Or you will uh, make your own data set. It will be in other forms. It will be it will not be a Python list. It will be a pandas data frame. It will be a CSV file. It will be all of that. Now, none of those are accepted during training. So in training, we deal with matrices, right? So what happens is we usually use an object defined in PyTorch as the data set. So as you can see from torch.utilities.data import dataset. Now this is the standard container in which our data should be contained for a machine learning model to be able to use it. And our data currently is not of type dataset. So dataset is a class, right? And this is the container in which our data should be, right? Usually we can use an autoloader for data sets that are larger than this and are in other formats. But for our case, we are improvising by making a custom class, which is a child of which inherits the class dataset, and it has the three necessary functions that the class dataset has, which is get item, len, and init. Right now, yeah, don't pay much attention to this, but just know that this is not usually the standard process. But this is only because we are using our own synthetic dataset, right? But after that, now we are here using our custom class, custom dataset to make our dataset, right? And we put it into train dataset. Now, usually what you will do, you will use a function like train test split on your dataset object or your pandas object or all of that. But right now, since our data is synthetic and our data is very small, we are using this custom object. That's all you need to know for right now. Now over here is the main part we should be focusing on our training arguments. Now, how will we train? Now, let's first of all go over that. So, transformers has an trainer object. So, what the trainer object does is it automatically runs all the epochs and the batches for us. And a trainer needs some settings, and those settings are defined by training arguments. So, what are those settings? So, first of all, per device train batch size. So, this means if you are running multiple devices per device, what should be the size of your batch? So what is a batch? So our data set has, let's say, n data points. Now we cannot process all n data points at once individually for a machine to learn. So what we do is we group those n data points into batches. So each batch in this case will have 4 data points, and we process 4 data points as one. That is what a batch is. So this is defining the batch size for each device, right? Gradient accumulation steps too. So what this does is, so a gradient is what allows us to, you know, change the weights of our model and, calculate the loss. Essentially, we'll get to this, but what it's saying essentially is that calculate the gradient, which is used to update the loss after every 2 steps. So by default, it will be 1. So after every step, update our model, but we have set it to 2. So learning rate is 2e minus 4. So what is 2e minus 4? So learning rate is, the magnitude. So let's say our, so we, so let's say our, trainer knows that we want to change our weights in a certain direction, right? Learning rate will tell us how many steps in that direction should we take. That is what a learning rate is. Now, a learning rate is usually small. So 2e minus 4 is a very small number, and that is what we'll be using for us and for our tiny data set. Now, this is all of this also depends on the type of data set we have. We have a very small data set here, so we have a small batch size. We are not updating, every single step. We are not updating the gradient. Our learning rate is also pretty small. So this is medium range for LoRa. And then we have number of training epochs. So an epoch is when you go through the entire data set once, that is called an epoch. After you go through the entire data set and update your weights, that is called an epoch. So in each epoch, we will go through the data in batches, and after the entire data set is complete, that will count as one epoch. Right, weight decay, let's ignore it. Logging steps 1 means that logging just means, the output of what the model is actually doing after every one step. Save strategy, we don't want any save strategy. Now, all of these are optional. Actually, you could have just removed them and it would have worked the same, right? Now we have our settings ready. How we want to train? We have defined our batch size. We have defined our accumulation steps. We have defined our learning rate, epochs, weight decay, not necessary here, 0, logging steps, and all of that. Now we initialize the trainer. Now the trainer takes certain arguments. What model we are going to train? which is the model we have defined earlier, Quen, Laura initialized, the arguments which we have defined over here, the training data set which we have defined, when we were formatting, right? And the data collator is the default data collator which is present in transformers. So this is also, I'll be skimming over this, but what a data collator actually does. So of course, in a larger data set, you would use a data collator, a dedicated data collator. But because our data set is very small, we are using the default one. Otherwise, you would import a data collator from PyTorch, right? Uh, so what data collator does is that what encoded it is that it converted into tokens, right? But that was per example. What a data collator does is that it adds padding for the entire data set, is essentially what it does. All right, and we have also specified what tokenizer we want to use, and the tokenizer we want to use is the tokenizer we defined earlier. All right, so these settings will be a bit confusing to you right now, but once you get a bit more familiar with machine learning, all these settings will start to make sense. So my advice over here would be, to make your own projects and do all of that and play around with these settings. So, change the per device training batches, change it to 5, change it to 6, change it to 7. See how it affects your use case, right? Change the gradient accumulation steps, change the learning rate, and you'll get a sense of what each one does. And even more than that, read the documents, read the documentation for whatever library you're using. So for instance, I'll just show you something really quickly. Should be visible to you. So you can just go to, so for example, I'm using Hugging Face Transformers libraries. You can just go to documents, and if I don't understand something, I can just search it. So what kind of task I'm doing? I'm using this library Transformers, so I can just click on Transformers, right? And it will have every single thing I want, reference for every single thing. So, let's say for training, right? Then I can go to trainer API, then training. Now over here, they will tell you, what training arguments is, what each one will do, right? And so if you are confused about any step, you can just refer the docs and, just check them to know what each line is doing, because there are a lot of arguments and each one does something. And so this you get with experience. But other than that, if you want to ask anything, I'll answer that. I know it can be a bit confusing, but don't worry. Is this much clear? Okay, says yes. Kanika as well. Anshu, Mohit, yes, okay. Okay, all right. I know this might be getting a bit tiring, so now let's switch over to some theory right now. We'll get back to our code. Or actually, the code is not left a lot. So now we have defined everything we want. We have our trainer, we have the training settings, we have our data. We have the three things we need. We have our model, we have our tokenizer, we have everything. So now the next logical steps is to just train or train. And what this outputs is that after each step, we get the training loss. And as you can see, the loss steadily decreases. We start at 5.29, and after 35 steps, we get to 1.12 loss. So our loss has decreased, right? So now this is the actual fine-tuning process. So after a lot of setup, we call a trainer and it does the fine-tuning process, right? It uses our data, it uses the tokenizer, it uses the data set, and now our model is fine-tuned. All right. Now we can actually evaluate our model. So our training loss was this much, 2.24. I'll get to what this means. I'll get to what PPL and train loss means. But right now, let's just, for something easier, let's look how our model performs now on the original prompts. So these were the prompts we used before fine-tuning. Turn to Shakespearean. Hello, how are you? The weather is nice today. Is that your pen? So these are the three prompts we used. And now the expectation is that the model will perform better than it did without fine-tuning, because we have done fine-tuning. A few key points we need to keep in mind is, first of all, the model's capability. the model we are using is not that advanced. It only has 3 billion parameters. And second thing, so it's not that capable. But the second thing being, is our model performing objectively better than previously? Now that objectivism comes from mathematics, but we can also intuitively check if it is performing better by just looking at the output. So I have the original prompts, I get their outputs. Let's see what we. So the first prompt was, hello, how are you? Now the output here is, how doth it fare with you? Now this is a lot better than we were getting previously. Previously we were getting just a bunch of gibberish. If I can just pull that up really quickly. So for the first input, the output previously was, how do you do? Hello, how are you? How do you do? How do you do? Hello, how are you? This is a playful and creative. So this was not up to the mark, but after fine tuning, we can actually see a noticeable performance gain, which is a single sentence that is consistent with what we wanted. So this is Shakespearean style. So the word doth is Victorian English, right? And the framing is also much like what Shakespeare would use. The second prompt was, the weather is nice today. And now this one is better than the previous one, but still not perfect. Now this, we can, let's go out for a picnic. The weather being pleasant today, let us venture forth for a picnic. Right. So we can see traces of Shakespearean style. So it uses some complex words, but this is, I would not use this, for my business application. I would just use a bigger model if I had to do that. But it's still better than what we got previously. Previously, we got a bunch of gibberish if we just go back to our previous results before fine tuning. Now, previously, the output was, what a lovely day it is. Let us go out and enjoy the sunshine. Can you suggest some activities we do outside? So as you can see, we do not want this extra text. So after fine tuning, it understands that we do not want that, and it gives me an appropriate output. Now this is still not perfect, but better. For the prompt, is that your pen? Now this output is not too well. I don't have a pen. How about you? Is it your quill? I do not possess a quill, as it were. What about you? Now it still stuffs a lot of tokens that we do not want. So I don't want this sentence. I don't have a pen. I just want this. Is it your quill? Because that corresponds to, is that your pen? All of this is not required, but this is still miles better than what we were getting previously, which was, yes, it is. That's a great way to start a conversation. Here's an example using Shakespearean style you mentioned, right? So it's better than what we had previously. So now we can see noticeably, using our own intuition, that we actually did improve on base model performance after fine tuning our model. So let me pause here and ask all of you, is this much clear? Mohit Yadav asks, how much time will it take to complete the session? Mohit, we will continue till 8 o'clock. And if we cannot complete till 8 o'clock, don't worry, we'll just have another session, right? Because I don't want to bore all of you over here. So we will be concluding soon enough. All right, okay, says it's clear. To others, is it clear? Are you able to see the difference we have after fine tuning? Yes, Kanika also says yes. Okay. All right. Okay, all right. Now this concludes our coding part. Now there are some more nuances we need to cover in terms of the theory, because we have not gone in depth on actually what this process of fine tuning does. So what is the mathematics behind this and what is actually happening? What's the time right now? It's 7:40. So actually, let's have a vote, because I also don't want to, bore all of you, because this information works well when it is bite-sized. So if you want that we continue in the next session, or if you want that we continue right now, let's have a vote, because I know it can be a bit overwhelming. So first of all, those of you who, yeah, and, okay, also, I also need to go over this point. We will also provide you cloud credit soon. I'll also go over this point, but first let's just have a vote that how many of you want that we continue right now? Right, yes. For those who want right now, right, yes. Hokesh says yes. Anyone else right now? Yeah, if you want to continue right now. Okay, all right. Those of you who want, we continue the next session now. Right, yes. Those of you who want, we continue in the next session. Mohit says yes. Chinmay also says yes. Anubhav says yes. Anubhav also says that we should continue in the next lesson. Everyone else who is there in the meeting. So if you are actually there, Arshleen, Chirag, Shatakshi, Kanika, Nandini, Aditya, Roshan, and Anshu. Okay, all right. I think according to majority vote, Kanika says I'm okay with both, but next would be better. All right. So we have 4 votes for yes and 1 vote for right now. Okay, all right. So I guess we will continue in the next session. But before that, before concluding, there are a few points. Yeah. Before ending, can we quickly provide them cloud credits? Yes, yes. So that's also a point we need to cover. So I'll just show you something. Um, okay, all right. So what I wanted to tell you, is that first of all, in your syllabus, there was a lab. There are multiple labs actually. So those labs require that you have cloud credits. So what that lab is, I'll just show you what that lab is. Um, All right. So, for example, this is a lab that we have in the syllabus, supervised fine tuning with Gemini for image captioning. Now, to access this lab, when you click on Start button, you will need a credit, right? Launch with 1 credit. So, uh, previously we did not have access to these credits, but right now we have Google has provisioned with us with credits. So you can claim your credits and you can actually start doing this lab. I wanted to also cover this, what was happening in this, but I guess we'll cover it later. So that was what I wanted to say to you. So you can complete your labs because you now have access to credits. Mohit says I have 650 cloud credits on arcade program. Yeah, Mohit, then yeah, this is just a single credit. You also don't need to. But I think Naman, it was $5, if I recall correctly, of worth of credits that have been provisioned.
This is about Google Cloud credits, not Skills Boost. Right. I think you have Skills Boost credit, Mohit.
Oh yeah, for the arcade program, that would be that one.
Yeah. Okay. So just can you just check my DM? I've sent you some instructions for how
Okay,
to
wait.
claim these.
Let me actually say.
Since this is being recorded, so we will not show you the whole process because there's some sensitive information like the coupon code. But we will still show you how to claim the credits on Google Cloud, right? So Anshu will show you right now. Also, if there is any kind of confusion regarding claiming, so we will go through this once more in the next session, just in the beginning. So if anyone has any doubts, right?
Okay, so alright, I'll just show you where you need to claim your credits. So this is the website, right? um, the link will be shared to you and the steps will be shared to you. So you just log in into this website, and as you can see, there is this button, click here to access your credits, right? So make sure to use the mail you have used to enroll in this initiative, and then you can just click on this button, and it will lead you to Google Cloud, and there's some terms and conditions. And now you can see it tells me that after accepted them, that credit successfully applied. All right. So this is just the general step. It's easy actually. So just claim your credits. The instructions, particular instructions, and any doubts will be entertained on the Discord. All right. So um, if all that is clear, now if anyone has any kind of doubt, I'm here. Naman is also here. So ask away related to the session we just had or the credits. Anyone, anything? Anyone wants to add something to the conversation? Any doubts of any sort? You can ask right now. And if not, we will continue to conclude the session. I wanted to cover a bit more in this session, but naturally, this takes a lot of time. Okay, all right. I think nobody has any doubts. So, Naman, should we conclude then?
Yes. Should we send then the instructions on Discord or what? Should I email
Uh,
them?
I think, yeah, emailing them would be, I think, better. Okay, Anubhav has one doubt. Naman, we can discuss this after this call. Okay, Anubhav, ask your doubt. How to start or begin with machine learning? Okay, all right. So, Anubhav, I assume you are a fresher, first year or second year. So, if you want to begin with machine learning, I recommend you. Yeah, you are a fresher, so you are first year, right? So, if you want to begin with machine learning, I think the best way to do it would be, now there's a lot of mathematics, statistics, probability, all of that in machine learning. So, first of all, I recommend that you are comfortable with those topics. Maybe not in much depth, but you should be comfortable with general concepts in mathematics, like what are probabilities, what is a joint probability, what is a conditional probability, how do probability distributions work, because entirety of machine learning is built on statistics and probability, right? So if you know those basics, it will help you. Now, the second important point is that most of those mathematics is actually abstracted away by libraries such as TensorFlow, PyTorch, all of that. So you don't actually need to write the code for mathematics. As you also saw in our demonstration, all of those functions were provided to us. We just uh, had to know how to use those functions. So most of the time you will just be using these libraries. And if you want a concrete starting point, I would recommend you start with uh, the most basics of machine learning. So for example, there is a so first of all, you need to choose what kind of machine learning you want, because there are a lot of domains, right? Supervised, unsupervised, semi-supervised, and then inside that, you can specialize in one single model. You can specialize in RNNs or CNNs or regression models, or these language models that we have nowadays. So just pick a genre, I'd say. What kind of machine learning? So if you want to work with images, for example, go with CNNs, RNNs. Audio, you want to work with RNNs, choose that, and then start by making very basic projects. Follow guided tutorials, go through the documentation, and along with that use that. So you're asking like we should go through some YouTube video tutorial, or would you recommend some course like how you have started? So all right, so for me, what I did, so for the mathematics part, I just read some books for that mathematics. But if you want, so there's a very good course by Andrew Ang on Coursera, which I'll just link in the chat right now, which will guide you through the basics of deep learning. It is a very informative course, and I will warn you, it is also mathematics heavy. So if you want to, choose deep learning as the area in machine learning you want to do, it will be it will be a very good resource for you. So for me, I do deep learning, I don't do classical machine learning, right? So wait, let me just check that. I'll give you the link of the course. Just 1 minute. Okay, actually, I'm not able to find it, but don't worry, I'll link it to you. Okay, I'll link it in the resources. It's a very good course. Hello, I have tried to claim the credits. I've tried to claim the credits, but can you tell me what to do after slide for accept and continue? So after you click on continue, there's the strip down there. It tells you that credits have been claimed, right? There is just one more step you can do. You need to do, which is set your account billing to Google Cloud Platform trial billing account. There, you can actually just follow the steps in the PPT. It will guide you. So the credit successfully applied dialog should have appeared if you clicked on accept and continue. And then if you will check your credits, it will show you how many remaining credits you have. So $5 worth of credits you should have after that. And then after that, just so you can start using that. So if you are confused as to, so first of all, you should be able to see you have 5 credits in your credits, $5 credits. And I once said check Discord, I have sent detailed instructions as well. How this cloud different than Google Skills Cloud Computation Program? Anubhav, I don't know what is the cloud computation program, so I'm unable to answer that. But this is machine learning oriented. So many of you might have doubt if this is a ML thing, then why do we need Google Cloud? So for models such as Gemini, Google allows us to fine tune them on the cloud platform only. So you cannot actually fine tune Gemini on Google Colab, the latest version. I mean, for to fine tune to Gemini, you need to have a Google Cloud account, set up a project there, and then in the cloud account you have the Google AI library, which is Vertex AI, which handles everything AI for Google Cloud, and using that only you can do whatever you want with Gemini. So that's why we need cloud access on this one. Okay. All right, so anyone else, anything else? If you want to ask, right now is the time, or I think we should close now. Okay, all right. So, okay, thank you guys for
I have
attending.
hello.
Yes, someone
I
said,
have got a yes. I have got an invitation from Dev Ecosystem Communities. Is that from you guys?
dev ecosystem communities.
Like in my Google Cloud, that skill boost settings.
Yes, that one is our, yeah, the dev ecosystem communities, right? That one is ours. So you can join that.
I got just an invitation, so I think I should accept that one.
Yes, you should accept that because that is ours.
Okay, that's
Okay, all right. So okay, thank you guys for attending. So I'll see you in the next session. Okay, bye.